All right, the count in a culture of bacteria was 400 after 2 hours and 25,600 after 6 hours. So in part A, we're supposed to find the relative rate of growth of the bacteria, so that R, and then also give it as a percentage. So as far as relative growth rate is concerned, we have N of t equals N naught E to the RT, and they're wanting us to find that relative growth rate. So they didn't even give me the initial population of the bacteria. However, they gave me these two pieces of info. 400 bacteria after 2 hours, 25,600 bacteria after 6 hours. So in a sense, I can just think of that as, I guess, ordered pairs that they're telling me about. So I'll say this is the info they are giving me. 2 hours later, there were 400 bacteria. So this is T, this is my N of T. And 6 hours later, there were 25,600 bacteria. So this is T, this is my N of T. So I do have some information that I could use and plug into my model. I'll go ahead and do that and plug in. I guess I do know the time and I do know the number at that time. So those are the two pieces that we're going to plug in for each one. So 400 bacteria occurred after 2 hours. And the other piece of info I'm going to plug in is 25,600 bacteria occurred when I had 6 hours go by. So basically, I'm using the two ordered pairs on that growth model to figure out what my N naught and R are, I guess. I don't know what they are. So here's one equation. 400 equals N naught e to the 2R, and 25,600 equals N naught e to the 6R. So I have two unknowns, two equations. I should be able to solve that and be able to tell what the R is, the relative growth rate. And also part B gets answered as well, because they also want us to find the initial size, which is the N naught. So you can use a substitution method if you want, your choice. I think I'm going to use that little trick of dividing two equations. So I'll take the one with the higher exponent and divided by the one with the lower exponent. That way I can eliminate the N naught altogether. So I'm going to divide the two equations because conveniently N naught disappears. I'll get a number on this side. 256 divided by 4, I guess, is 64. And on the right side, same base, subtracting exponents. 6R minus 2R is e to the 4R. So again, you can do a substitution if you want, isolate N naught and plug it into the other equation, or you can use this trick of dividing the two equations. Now I'm going to solve for R by taking ln of both sides. These guys cancel, so I have ln of 64 equals 4R, and dividing by 4 will help me get my relative growth rate. So R is ln of 64 over 4. Let's punch that in. We're going to get ln of 64 divided by 4, which gives us 1.0397. Let's say it goes on forever and ever. So that's the R in decimal form. Remember, whenever you do math with your R, what you're getting is in decimal form. You're either getting an output in decimal form for the rate, or when you go use it inside a formula, you make sure you convert it as a decimal and you put it in. So my calculator is spitting it out in decimal form, but the problem says express it as a percentage. So to change it to a percent, I got to take that decimal and multiply it by 100, and that's going to give me the final percentage increase. So I have 103.9 and I guess 104% relative growth rate is what I'm looking at, since they said give it to me as a percent. So if I only had like 0.03, that would be a 3%. If I had 0.50, that would be a 50%. In this case, it's over 1, so it's over 100% for the relative growth rate. So that was part A. Part B says, what's the initial size? That's my N naught. That shouldn't be a problem since I have two equations to go to and use my R value that I have found. So let's say I go to maybe this equation. Doesn't matter where I go to, I'll get the same answer. Let's say I go to the one with the smaller numbers involved. So for part B, let me put it on the side. I have 400 equals N naught e to the 2R, but we found our R value to be 1.0397, let's say. So I have to divide both sides by that number, whatever that number is. These guys cancel, and my N naught is going to be, can go punch it in quickly. It's going to be 400 divided by e to the 2 times 1.0397. So it looks like I have, I guess, if I just round to the nearest number 50, I'll end up with, or I started with 50 bacteria was the initial amount. And again, since I had two equations, two unknowns, I was able to find the unknown R and the unknown N naught. So the initial population or bacteria culture was 50. Part C says, find a function that models the number of bacteria n of t after t hours. Well, that's pretty straightforward. If I have the initial amount and I have the relative growth rate, I just go plug it in to my function. And here I have it, n of t. I started with 50 bacteria, and the relative growth rate was 1.0397 t. Remember, I'm inputting it in decimal form for my formula. Or if you wanted to look at that in terms of what is the growth factor of something that has that big of a relative growth rate, that's a big growth. Let's go manipulate some exponents there. I could think of that as 50 e to the 1.0397 raised to the t. Because remember, if I multiply two exponents, power raised to a power, I'm going to get this guy. So all I did was I put the 1.0397 inside and I yanked the t outside. Now that will tell me what the base is. If I go punch that into my calculator, I'm going to have e to the 1.0397, and that's going to spit out a pretty big growth rate, 2.8 if you rounded almost 3. So that bacteria pretty much triples every hour, because a relative growth rate of 104% apparently is comparable to a 2.82 growth factor. So 2.83, let's say, if I round it to 2 decimal places. This model can also be written in terms of its growth factor, 50, 2.83. I mean, you don't have to do this, but it's a good exercise to see how the same population can be modeled with different equation that gives different information about it. So this population almost triples, because 2.8, if I round it, is close to 3 every hour, having a relative growth rate of 104%, so increasing by a 104% at every moment. Okay, so again, this is good enough. You're done here. what I did here was go one step further and kind of figure out, wait a minute, a relative growth rate of that amount, what does it signify in terms of growth factor? That means every unit that you take on your data, a table of data, you're multiplying the previous one by 2.83. Part D says, find the number of bacteria after 4.5 hours. Well, we can go use the one that we found in terms of our relative growth rate and just plug in 4.5 hours. And if I even plug 4.5 hours in the other one that I made up, I would get the same answer. So that's going to give me 50, 4.5 hours later, e to the 1.0397, put in a 4.5 for your time. Let's go punch that in. 50 e to the 1.0397 times 4.5. And that's going to spit out a 5381. So we've got 5381 about bacteria after 4.5 hours. Notice we only started with 50. We know it's tripling every hour, almost tripling every hour that goes by. And in just 4.5 hours, since we've got a pretty big growth rate and a big growth factor, we get 5381 bacteria. Last part says, after how many hours will the number of bacteria reach 50,000? So now I'm looking for time. I have the output of 50,000. So for part E, I'm going to start with the same model. And I'm going to put 50,000. I want to know when it reaches 50,000. And now I just have to solve that exponential equation. So let's divide both sides by 50. That's e to the 1.0397t equals, we end up with 1,000. If I take ln of both sides, I have ln of 1,000 equals 1.0397t. So I'll divide both sides by 1.0397, and we're going to figure out how many hours later there were 50,000 bacteria. So we've got ln of 1,000 divided by 1.0397, and it looks like in about 6.6 hours we ended up with 50,000 bacteria. So about, let's say, 6.64 hours later we had 50,000 bacteria. So you want to keep in mind that when you're talking about these growth problems, you can have different equations represent the growth. It could be in terms of its growth factor, in terms of its growth rate, or even in terms of its relative growth rate, or as we saw in the previous examples, in terms of its doubling time. But the process is pretty comparable. Once you find your model, you either plug in the time or you plug in the number of your population to get the time. In this problem, probably the hardest thing was part A, which was use the two ordered pairs from the information given and solve a system to get your relative growth rate and your initial amount. And that's it for example 6.